All living cells are surrounded by a plasma membrane composed of a lipid bilayer. The hydrophobic core of the lipid bilayer prevents movement of ions across the membrane. This property allows a cell to maintain different concentrations of ions on either side of the membrane. The only way ions can diffuse across a lipid bilayer is by passing through specialized channels. These channels are transmembrane pores that permit the movement of particular ions while excluding others. Channels can be in an open or closed state. Consider a simple system in which an artificial membrane separates two compartments containing a 1 millimolar potassium chloride solution. If the membrane is permeable only to potassium ions, depicted as orange spheres, and the concentration of potassium on each side of this membrane is equal, then no electrical potential will be measured across the membrane. However, if the concentration of potassium is not the same on the two sides, then an electrical potential will be generated. This potential is generated because potassium ions flow down their concentration gradient from compartment 1 to compartment 2 and take their electrical charge, one positive charge per ion, with them as they go. Because the potential gradient across the membrane tends to repel the charged potassium ions, it tends to impede further flow of potassium ions. Thus, as compartment 2 becomes positive relative to compartment 1, the increasing positivity makes compartment 2 less attractive to the positively charged potassium ions. When the two forces are in balance, there will be no net movement or flux of potassium across the membrane. Thus, for a given permeant ion, there is a voltage at which a diffusional force, produced by the difference in internal and external concentrations, will be exactly balanced by an electrical force in the opposite direction. At this point, there is no net driving force, and hence no net movement of the ion. The voltage across the cell membrane represents the equilibrium potential, E-ion, for the permeant ion. The Nernst equation brings together descriptions of the equal and opposite electrical and chemical forces that act on the permeant ion. It allows us to calculate the equilibrium potential from the internal and external concentrations of any ionic species. We can simplify the equation by entering the values for the constants. Note that the units for the Nernst equation are joules per coulomb, which is the same as for volts. Because it's easier to perform calculations using base 10 logarithms and to perform experiments at room temperature, this relationship is usually simplified to where log indicates the base 10 logarithm of the concentration ratio. When the cell is at rest, the most permeant ion is potassium. If potassium is the only ion moving across the cell membrane, the resting potential should be identical to the equilibrium potential for potassium, Ek. We can now apply the Nernst equation to determine Ek for a squid giant axon. According to the Nernst equation, the equilibrium potential for potassium is minus 76 millivolts. However, when we record the resting membrane potential of a real squid axon, we obtain a value of around minus 65 millivolts. Why is there a discrepancy? Is the resting potential really driven by potassium ions? If the resting membrane potential of a cell is driven by potassium ions, then we should be able to change the membrane potential by altering the concentration of potassium in the solution bathing the cell. This is because changing the external potassium concentration alters the concentration gradient for potassium across the cell membrane. When we record the membrane potential while changing the external potassium concentration, we obtain the result shown on the graph. Note that as the potassium concentration in the bath rises, the membrane potential also becomes more positive. In qualitative terms, the results show that potassium ions indeed regulate the membrane potential. As the external potassium concentration is increased, the difference between internal and external potassium levels decreases. This causes the membrane potential, Vm, to approach 0 millivolts. This graph shows the relationship between resting membrane potential and external potassium concentration plotted on a semi-logarithmic scale. The straight black line represents a slope of 58 millivolts per tenfold change in concentration, as given by the Nernst equation. The red line shows the data from our previous experiment. What might explain the discrepancy between the data predicted by the Nernst equation and the observed results? The discrepancy between Ek and the true resting potential comes about because the Nernst equation takes only a single ion into consideration. Although potassium is the most permeant ion, it is not the only permeant ion. There is a small but significant permeability to sodium and chloride ions in the resting cell membrane. To calculate the true resting potential, we have to extend the Nernst equation to incorporate terms for other permeant ions, taking into account the fact that not all ions are equally permeant. The equation that allows us to do this is the Goldman equation. The membrane potential, Em, is calculated based on the concentrations and relative permeabilities of all classes of ions that cross the membrane. Like the Nernst equation, the Goldman equation reflects the ratio of external to internal concentrations for each permeant ion, sodium, potassium, and chloride. It also includes their permeability coefficients, pNa, pK, and pCl. These terms reflect the intrinsic ability of each ion to cross the cell membrane. If the membrane is permeable only to potassium, then pNa and pCl are both zero, and the Goldman equation collapses down to the Nernst equation for potassium. To account for the small but significant movement of sodium and chloride ions across the membrane, it's useful to reformulate the Goldman equation in terms of permeability of each ion relative to that of potassium, since potassium is the most permeant ion. Typical values for the relative permeabilities of sodium, potassium, and chloride are 1.00 to 0.04 to 0.45. If we now incorporate the concentrations for each of the three permeant ions, we can apply the Goldman equation to calculate Em, the membrane potential. Does the Goldman equation predict the membrane potential more accurately than the Nernst equation? The calculated Em is approximately minus 62 millivolts, which is very close to the minus 65 millivolts that we measured from the squid axon with our recording electrode. The slight discrepancy is due to the operation of an ion pump in the neuronal membrane.